All right, so thank you everyone for coming today. There's a lot of people, which is wonderful. And thank you to the organizers for having this terrific meeting. I think that in the past, we used to talk, mathematicians and artists used to talk, going back to the origins of projective geometry and even further, and so we may keep up those conversations today. So my talk today is about the interface of algebra and geometry. Most of my work concerns the interfaces of different parts of mathematics with one another because I'm interested in both the way that these areas are distinguished from one another and the ways in which we think in each of these discrete areas and the ways in which we can then learn to think differently from interacting with these areas. So I'm interested in these questions in lots and lots of areas. In particular, lately I've been thinking a lot about algebraic geometry in the contemporary sense, but of course to think about that, we have a lot of presuppositions that are built into our thinking that go to the origins of the subject. And so today I want to turn ourselves back to the beginnings of that subject matter in thinking about Descartes. So now I have to see if this little thingy works. Because if not, then we have to figure out some other way to do this. Well, certainly that will work. So this talk concerns, as I say here, the relationship between the synthetic or constructive reasoning that's typical of classical geometry, and then by contrast, the algebraic reasoning that's central to geometric practice since Descartes. And I want to think of these as focal questions. On the one hand, did this broadening of geometrical methods to include algebraic methods signify a shift in the type of knowledge that we sought as geometers? Or should we think of these expanded methods as being rather a better way to accomplish the same ends, the same knowledge we sought classically? And I want to defend, or at least try to defend, the thesis that it does represent a shift. And the shift will be, in summary, a shift from thinking about the knowledge that we gain from constructing solutions to problems, that's the classical mode of knowledge geometry sought, to knowledge of what Descartes will call the natures of problems. And so I'll talk about that today. So because this is a short talk, I can't say very much about the ancients, but I'll say just a little bit. There's lots that we don't know about what they thought. But in as much as we can see that there was some kind of consensus, there seemed to be consensus that the knowledge of configurations that were produced by constructions in geometry, the knowledge was warranted only to the extent that the constructions were sufficiently simple. We don't have a lot of careful specifications of what the ancients considered simple. We do know, as everyone knows now, that constructions by ruler and compass were considered sufficiently simple. And we know that other constructions that use the two curves called the spiral and the quadratrix, these curves were judged insufficiently simple. Pappus called them rather mechanical. And the diagnosis seemed to be on the basis of the type of complexity that was involved in their motions. In short, to construct a spiral, you use two independent motions. And the thought seemed to be by the ancients that this was too complex. Too complex in what sense? Well, this is the mystery, I think. You find occasionally texts like Proclus, for instance, who say things like, well, it has to do with the mystical ordering of things and the planets obey the basic laws of simplicity. And you start to wonder, where is the point? And that's the problem. Proclus had an agenda. He was a Neoplatonist. He was the director of Plato's school in late antiquity. So he was trying to drive home a program. We don't have a lot of anything clearer to say from the ancients, as far as we know. These texts, if there were any, were lost. So they just don't tell us an answer to the question about what type of simplicity was being measured. Now I want to shift the talk. So take that to be the status quo about the time that Descartes gets to do his work. So now let me tell you a little bit about Cartesian problem solving. So there are two steps in Cartesian problem solving. First, what he called analysis, which was to reduce a geometrical problem to an equation, to an algebraic equation. And then the second step was what he called synthesis, which is the construction of the roots of an equation. Let me give you an example of such construction, of such solution. So here is a classical problem, the problem of triangle division. It's an easy problem. Given a triangle and a point, which I've designated by D, lying outside the triangle, draw a line through that point that divides the triangle into two equal parts. So here's that the one I've drawn there is supposed to be an example. So now let's see, the ancients had a solution to this. Let's see how Descartes solved this problem. So the first thing you do is you suppose that the problem has been solved. This is characteristic of analysis. The line DH that I've drawn there, we suppose is the solution to the problem. So let's say that it intersects the bottom of that triangle, the base BC, at the point I. I can use my little laser thing here. Now, we want to construct a line. So the next step is to construct a line through D that's parallel to BC, and it will intersect the extended leg of the triangle here at this point E. And now we use facts about similar triangles. So we have that this triangle here and this bigger triangle are similar triangles, and we then can get ourselves a ratio that this quantity U is to P as Z is to Q plus Z, to this entire length here. And if we turn that into an algebraic equation, we just obtain this equation here. Now, since we suppose that this line divided the triangle into two equal parts, we have a Euclidean theorem we can draw on, which tells us that the ratio of U times Z to A times B is equal to 1 over 2. And we thus obtain a second algebraic equation. So I won't dwell on too much of the details there, but they're fairly elementary inferences from just Euclidean geometry. Now, what Descartes does then is you say, well, we have two equations in two unknowns, and so we can convert that then into a single equation by eliminating one of the variables, and we obtain a quadratic equation. And then that finishes the analysis, and then what you have to do, which I will suppress for the time being, is to construct then the roots of this equation, or one of these roots, as a line segment, and that will then finish the construction. So this is what Descartes calls the synthesis. Now he gives a procedure for doing this. For any equation of this form, for any quadratic equation, Descartes has given in the geometry, his textbook from that comes at the end of the Discourse on Method from 1637. He's given a procedure for constructing by ruler and compass the solution to any quadratic equation. And so all it would take to do would be to apply that one solution he's already found to this particular equation. So now that's an example of that's the Cartesian problematic here. And I want to argue that this move in Cartesian geometry is a shift in the kind of knowledge that the geometer seeks. Because what it is, in summary, the geometer comes to obtain knowledge of what curves best promote clear and distinct syntheses. So the thesis I'm trying to defend today, which I'll then now give you evidence for, is that algebraic knowledge helps us discover classically valuable solutions to problems. And that in fact, this knowledge can be an end in itself, that carrying out the construction ourselves does not increase the value of this algebraic knowledge. But these things are best given flesh in the presentation. So here's another problem that I think makes these things more vivid. So here's an ancient problem, Apollonius' problem of the three circles. The problem is, given three circles in a plane, construct a circle that touches all three circles. And here is one particular configuration of the Apollonius problem when the circles are in a triangular configuration. So this is from Descartes' correspondence. This is the diagram that he drew. Now, this problem, we have reports that the ancients had a ruler and compass solution to this problem, but we don't have a copy of that solution. However, in 1600, the French mathematician Viette had given a ruler and compass solution, but at Descartes' time, no solution by algebraic analysis was known. And so what Descartes does, he has a lively correspondence with Princess Elisabeth, and they talk about lots and lots of things, the mind-body problem. It's very, I just had students read this semester, and they enjoyed seeing how much back and forth there is between Princess Elisabeth and Descartes. He's quite mean to her, and she's quite mean to him. It's really lively. And I think it's best to understand this problem in the context of that correspondence, because what Descartes does is he suggests to Elisabeth that she practice her algebraic skills by finding an algebraic solution or analysis of this problem in this particular case. And he himself has already done this, so he knows what she's getting into. And He then, in correspondence, lays out how you could do this. So this is a somewhat complicated-looking representation of the Cartesian solution. So what you do, in short, is you apply Pythagoras' theorem to right triangles that you obtain in this diagram, and you'll get three equations in three unknowns. And then what Descartes does is he says, firstly, you could reduce these three equations to a single quadratic equation, but he doesn't actually find that single equation in the correspondence. And then he concludes by saying that he had already given a procedure in the geometry for finding ruler and compass solution to quadratic problems, as I explained to you earlier. And therefore, he doesn't apply the solution here, once again. Well, he's being a trickster, I think, because using Mathematica, Henk Boss was able to compute what the equation would have been had Descartes actually, had Princess Elisabeth carried it out. So as you can see, it's quite a ridiculous situation. This is what Princess Elisabeth would have done for homework if Descartes had been a good teacher. And of course, he doesn't do it either. You see this has 87 terms, and each of the terms is a product of 6 factors. So there's an extraordinary amount of complexity in Cartesian analysis. And so Descartes himself, though he preaches the value of doing this, he doesn't carry out all of the computations himself. So here's what he tells her in the correspondence. So he tells her, so I'll read this passage from him. He says, by substituting a single letter instead of several, as you have done here very often, the calculation will not be tedious. This is something that one can almost always do when one wants to see what is the nature of a question, i.e. if it can be solved with ruler and compass, or if it is necessary to use some other curves of the first or second genus, and what is the way for finding it, which is what I ordinarily content myself with regarding particular questions. For it seems to me that the surplus that consists in seeking the construction and demonstration by means of the propositions of Euclid, while hiding the algebraic process, is but amusement for little geometers, which does not require much of either the mind or science. And this is a characteristic passage in Descartes' writings at this time, in correspondence with various people. You can tell the sneer, that characteristic Cartesian sneer, at those little geometers who do the constructions, while we ourselves concern ourselves merely with the algebra. So the thought seems to be that analysis gives us the nature of a problem by exhibiting an equation, and that this is a useful, proper strategy for the mind. But the construction would be barren for the mind to carry out each of those steps. And he put this point, I think, nicely in a 1638 letter to Mersenne, where he says, I make the construction like architects make buildings, prescribing only what to do, and leaving the manual work to the carpenters and masons. Once again, that Cartesian sneer. So at this late date, and the reason I say at this late date is because by 1638, 1643, Descartes has gone, most of his work in algebra begins around 1619. So he's been doing work for quite a while now, and his views shift a lot. And here, by this point, he's interested in finding the nature or form of problems, an algebraic feature. Now, you could take a kind of cynical view and say, well, the reason he was concerned with that is because he knew how difficult the calculations would be otherwise. But I think that there's, as in Descartes' case, there's always mixed motives. And another motive is the epistemic view that I'm about to show you. What type of knowledge does this grasp of the nature or form of a problem represent? And as I told you earlier, I think that the purpose of identifying the nature of problems is to determine what curves to use in a synthesis, even if we don't, in fact, carry out that synthesis. The knowledge is a knowledge of discovery, and then we leave it for the masons and carpenters or the little geometers to carry out the procedure. And I think there's some evidence for this view if we look at an earlier view that Descartes presents for us in the Rules for the Direction of the Mind. This is an unpublished text of Descartes from the middle of the 1620s. So here he writes in Rule 16 the following. He says, note first that arithmeticians usually represent individual magnitudes by means of several units or by some number, whereas in this context we are abstracting just as much from numbers as we did from geometrical figures a little while back, or from any matter whatsoever. We do this both to avoid the tedium of long and unnecessary calculation, and most importantly, to see that the parts of the subject relevant to the nature of the problem are kept separate at all times and are not bogged down with pointless numerical expressions. And now he gives an example in the regulae where he explains what he means here. So he says, for instance, consider the problem of finding the hypotenuse of a right-angled triangle where the sides have length 9 and 12. Okay, so easy problem for us. And Descartes says the arithmetician will say that it is the square root of 225 or 15, the length of the hypotenuse. But we, the algebraist, on the other hand, will substitute a and b for 9 and 12, and we'll find the hypotenuse to be the square root of a squared plus b squared, which keeps distinct the two parts a squared and b squared, which the numerical expression conflates. So the point here is that the arithmetician expresses the number, expresses the hypotenuse merely as a number, but Descartes, the algebraist, expresses it as a formula. And the formula is supposed to tell us not only what holds generally rather than case by case, but also how the hypotenuse depends on the two sides. And this dependency is obscured when we only draw or represent the hypotenuse by a number. So the algebra is meant to reveal. It's a mode of expression that reveals more than merely expressing as a number. So let's see then, what does this mode of representation buy us? Well, Descartes thinks it buys us additional gains as well. He says, we must note that, this is all just keeping from Rule 16, even though we are abstracting the terms of a problem from certain numbers in order to investigate its nature, yet it often turns out that the problem can be solved in a simpler way by employing the given numbers than by abstracting from them. So the claim here seems to be that we can find, once we have found the nature of the problem by an algebraic expression, we can then solve the particular problem that we sought to solve in a simpler and hence better way. So to do that, we go back to the original problem and we plug the numbers back into the equation that we have. So he says, continuing the narration, so what we do then is, since we have found that the hypotenuse of the right-angled triangle with sides a and b is the square root of a squared plus b squared, we substitute 81 for a squared, 144 for b squared, and we get 225 and find that the root is 15. The same thing that the arithmetician got. But we also gain more information, says Descartes. We'll see from this that the length of the hypotenuse, 15, is commensurable with the length of the other sides, 9 and 12. And this is not something that we'll generally recognize from the fact that we have the hypotenuse of a right-angled triangle, two sides of which are in the ratio 3 to 4. That is, there's an additional gain of knowledge that we have once we've revealed the algebraic form. And of course, this is an easy computation to see what he means. If we have sides in the ratio 3 to 4, when we plug them into our equation, we get that the hypotenuse, if a is equal to some 3 times n, b is equal to 4 times n, the hypotenuse will be equal to 5 times n. So whenever the sides are in this ratio, we can judge that the hypotenuse will be commensurable. That's a big observation, says Descartes. And we know this in every single case by a single deduction when we know the formula. We've incredibly compressed the need to find computation by computation. We've done it in one step. The arithmetician has to do a separate deduction for each case. Now, Descartes stresses that we insist on these distinctions, seeking as we do a knowledge of things that is evident and distinct. And this is what algebra seems to have helped us with. And now he makes an epistemic punchline, I suppose you could say. The arithmeticians, however, make no such distinctions. They are quite content if the sum they are seeking comes to light, even though they have no idea how it depends on the data. Yet that, quite simply, is what knowledge, strictly speaking, consists in. And here the word he uses for knowledge is this very strong word, scientia. For Descartes, you'll find in fact, as far as I know, this is the only text in the entire Cartesian corpus where he tells us what he means by knowledge. He spent all this work, all dialogue after meditation after meditation, talking about knowledge. Here in this mathematical example, in an unpublished work, he tells us what knowledge is. And the way we learn what knowledge is by thinking about the Pythagorean theorem. It's by thinking about algebra. It's by thinking about the nature of problems. It's by thinking about how the solution of a problem depends on the data. This is what we learn via algebra. So what does this mean when he says that the problem shows how the formula shows how the problem's solution depends on the data? Well, it draws our attention to the distinct parts of the problem's data. That is, it gives us a clear judgment in the Cartesian sense, and it shows us how the parts are related. That is, it's a distinct judgment in the Cartesian sense. So we can easily deduce that when the sides are in the ratio 3 to 4, the hypotenuse is commensurable with the sides in the ratio 3, 4, 5. From that, we can easily figure out that the hypotenuse is 15 when the sides are in the ratio 9 to 12. So we can avoid difficult computation when we know the formula. And we can do this in one case rather than step-by-step case, as the arithmetician must do. So this, he says, is what scientia consists in. We see how a solution to a problem depends on the data, where the dependence is expressed by a formula which shows how solutions are a function of the parameters of the problem. And he stresses that not only does this buy us then particular solutions to problems that are easy, it also buys us extra simplifications so we can show the commensurability in one blow, whereas the arithmetician takes many, many tries to show the same fact. So now, I've been talking about arithmetic for a while. Let's turn back to geometry. There is this passage I told you where he says that what we do in geometry is we find the nature of the question. And I want now to show you that I can explain what he means there by talking about what we just did in the regulae. So the claim here is that algebraic analysis shows you how particular problems, like the Apollonius problem, depend on their data. And what that means in the case of the Apollonius problem is that we find its nature, and by doing that, we learn the curves that we can use for a synthesis of that problem, and we learn what curves we cannot use for a solution to that problem. Again, modulo facts about the reducibility of the algebraic equation that we find. So we learn that linear and quadratic problems can be solved by ruler and compass, and we learn that cubic and quartic problems cannot. And then we can then direct our searches for syntheses better, because we know what curves to try and what curves not to try. We have improved our gain, we've gained in the efficiency of our search procedure for solutions. Even if we never carry out that search procedure, we've still gained something. We leave it to the Masons then to do their job even easier, but we ourselves have already accomplished our goal. So I want to say that in both cases, we've found an improved method of discovery. This was something that was very important to Descartes in mathematics, to find a method to answer every problem. It's a kind of rationalistic optimism. And he thought that this view that he had discovered in geometry was the key to this. It was a method of discovery. In the case of arithmetic, what we seek is an arithmetic computation. In the case of geometry, we seek a construction. But in both cases, the nature of the problem, an algebraic fact, locates a simpler solution to the problem. And as I just said, it improves our efficiency. Now, I want to handle a deep objection, which is to say, how could all this algebraic manipulation amount to discovering a synthetic proof to a construction? Wouldn't it be more plausible to say that what you discovered was just a bunch of algebraic manipulations? And I think that Descartes recognized this point and therefore had to change his view on what knowledge of geometry really was. So it wasn't that we came to know figures as figures, but rather we come to know figures in a much more general way, not as figures, but as quantities. And these equations then, the natures, or if you like, the definitions of the problems, they provide the content of the knowledge of figures that constitute the general knowledge of them as quantities. And so there's been a transformation in the content of geometrical problems in the background here. That the mode of discovery that Descartes invents is general, and therefore requires that its object be general as well. Even if, in the end, most people will be interested in this reasoning because it helps us discover specific classical constructions. But that, for Descartes, was no longer the primary interest. The primary interest was discovering knowledge of these figures as quantities. All right, so now just one slide in summary, and then I'm done. So just to tell you what I thought, the ancients thought that knowledge obtained by simple constructions was the valuable kind of knowledge, even though there seems to have been no ancient settled view on what such simplicity consists in. And Descartes himself seems to have been interested in that knowledge, but even more interested in this new kind of knowledge that geometry could engender. And this was knowledge of the nature of problems that makes clear the optimality of the particular degree of clarity and distinctness for solving a particular problem. This was knowledge that was valuable for guiding our discovery of synthetic solutions to problems, knowledge that even if we didn't deploy it ourselves was of value in and of itself. And of course, this knowledge depends on ancient algebraic reasoning of the sort that was not available to the ancients. And so it is a shift of knowledge. All right, then I'm done.